lecture is given by Chris Wrede. He's an experimentalist at FRIB. He has gotten his PhD at Yale University, he's originally from Canada, but came to the US. He did his postdoc at the University of Washington, and then he came to MSU, and he's running an experimental program measuring reactions that matter in stars, and he will tell us about that today.
Okay, thanks, Henrik, and thanks everybody for coming. Yeah, it's exciting to share what we're doing at MSU with you all, and I'm glad you signed up. So title today is Experimental Nuclear Astrophysics. That's our field with rare isotopes. Rare isotopes are a way of saying radioactive nuclei. Let's see, I am there we go, able to switch my slides now. Okay, so the outline here is I'm going to talk about experimental nuclear astrophysics, first of all, with stable beams, stable nuclides. Those are the ones that are not radioactive, and then move into experimental nuclear astrophysics with unstable nuclides, those rare isotopes I just mentioned. And then I'll talk about them at a particular facility, the National Superconducting Cyclotron Lab, which has been an operating facility here at Michigan State University, where Henrik and I both are up until now, and then rare isotope beams in the very near future at the facility for rare isotope beams at the same site. And then talk about some major experimental equipment planned for FRIB. So the subject today is the nucleus and stars. Okay, so on the left-hand side here, you see a little animation, I hope, of a nucleus with some electrons around it. So this whole thing is an atom, and nothing is to scale here. The nucleus would be a lot smaller here. But you have 2 protons and 2 neutrons in the middle, and then you have 2 electrons orbiting around. And we're going to focus today on the nucleus and its relation to stars. At first, stars like our sun that are undergoing some quiescent nuclear fusion burning in their cores to generate energy. And then later to transient astrophysical events, a lot of them explosive events. What you're looking at on the right-hand side is the remnant of supernova that happened hundreds of years ago when a star died. So we're already moving into our first question of the day. And so I think Anna is going to put that up.
Just a sec.
All right.
There it goes. Oh. So you guys pick, yeah, good.
Okay, and I'm not necessarily going to give you all the answers before I ask you these questions. Some of them are just to probe where you're at, so that what I say is more sensible afterwards.
Should I share results?
Sure, yeah. Okay, good. So most of you, all of you got that it's something to do with nuclear physics, and that is indeed the case. And a majority of you said nuclear fusion, and that's right. That's how the sun's generating energy. You're actually sticking together protons and turning some of those into neutrons in the process to make a helium atom like the one that we see on the left. Okay, so you all already have some intuition of what we're doing. Nuclear fission is big heavy nuclei splitting apart into smaller pieces, and that's not how energy is generated in stars like the sun. Okay, so a little bit more detail on the synthesis of elements in stars. In the sun, we have this step 1 here in the top left. That's hydrogen burning, where you're sticking together protons, the nuclei of hydrogen, and making helium. And that's what the sun has been doing for most of its life, and will do for most of the rest of its life. Eventually, you'll get to a stage where in the core of the star, in the core of the sun, it becomes hot enough to stick together helium nuclei, fuse them to produce carbon and oxygen. And ultimately, that's where the sun will stop, because it's not massive enough to get hot enough to burn things, to burn carbon and oxygen to heavier things. But if you have a somewhat more massive star than the sun, then you can start fusing carbon, oxygen, and neon to produce nuclei that have between 16 and 28 nucleons, so 16 and 28 protons and or neutrons in their nucleus. And if you get into a star that's about 8 solar masses or more, you might undergo silicon burning, which is really the start of the end of the star, where you can start generating an iron core in the star. So you're producing things mass 28 to 60, and the iron's kind of a dead end for that nucleosynthesis in the star that ultimately, or that has been supporting the star the whole time, and the star is likely going to explode as a supernova pretty soon once you enter that stage. There are other processes that enable us to produce the heavier elements, so the ones with mass higher than iron, roughly, and those are the slow neutron capture process, the rapid neutron capture process, and also the P process, which is likely a process in which a high temperature environment breaks apart nuclei into smaller pieces. And then there's some lighter elements that aren't produced in stars, like lithium, beryllium, and boron, that actually get produced in between stars, in the almost empty space between stars, when high energy particles like protons fly through space and hit another nucleus and break it into smaller pieces like lithium, beryllium, and boron. So on the right-hand side is one of our best observational.
Is it experimentally proven that these are, you know, let's say made outside the stellar environment?
Is it experimentally? I guess you mean observationally, observationally proven. You produce a little bit of lithium in the Big Bang. It's expected, and it's just difficult to produce any of these nuclei in stellar models.
I see.
That's one of the problems. I assume that measurements of cosmic rays can produce some constraints on how much lithium, beryllium, and boron are being produced by cosmic rays, because ultimately these become cosmic rays when they're produced by cosmic rays. So I think there's probably a consistent picture there. And then, you know, the measurements in the laboratory of the types of reactions that would take place to produce these are relatively easy to do as well. So I think the cross sections for their production is well understood, and you know, the contents of the cosmic rays that would be available to undergo those reactions, like how many protons are flying around out there, is pretty well known, and so is the amount of gas that's out there. So on the right-hand side here is just is a plot of the solar abundances. So we can look at the sun and do stellar spectroscopy to figure out how much of every chemical element is there, and that's what's being plotted here. So we're seeing the abundance, of elements as a function of nucleon number A. So how many protons or neutrons there are in the nucleus. So we're going from left to right. We're going from lighter species to heavier species, and you can see there's a lot more of the lighter species that are produced in stars, and a lot less of the heavier species that are produced in these neutron capture processes, for example, and really not much of those ones that are produced by cosmic rays. So the kind of playing board that nuclear astrophysics plays out on, and
slow process and rapid process. I mean, see, what do you mean by that? You know, is slow reaction or?
Yeah, good question.
Motion, what do you say?
Yeah, so maybe I'll point it out on this chart here. So this is the chart of nuclides here, which is kind of the playing surface for nuclear physics and for nuclear astrophysics. And what we're looking at here is a plot of the number of protons in a nucleus versus the number of neutrons in a nucleus. And all of the black squares here are the stable nuclides, the ones that aren't radioactive, and the ones that once you produce them stay around essentially forever, unless you try to transmute them in some way. And as we go away from those, become more and more unstable, shorter and shorter, until the nuclei ultimately become unbound and just fall apart the moment that we produce them. And so these processes that we believe produce the various nuclides in the stellar spectra and in the solar spectrum are shown on this plot here. Okay, and so we have stellar fusion down here producing up to mass 60 or so, and then we have this slow neutron capture process right here, which is this big diagonal line, which is in kind of a dark pink here. And that slow neutron capture process, it's slow because it takes place in an environment that has some free neutrons, but not a very high density of those free neutrons. So you'll start with some seed nucleus that might capture a neutron, and then thousands of years later capture our second neutron, and then thousands of years later capture a third neutron. And in between, if you're making anything radioactive, you're decaying back to a stable isotope by beta decay. And so you stay always very close to these stable isotopes in the slow neutron capture process. In contrast, if you can produce an environment, if a star or a stellar event can produce an environment with a very high density of free neutrons, then some seed nucleus can capture a lot of neutrons in a very short amount of time that might not even leave enough time for beta decays to happen in between. And in that case, you get pushed out to very neutron-rich territory out here, represented by this blue line. And that is the rapid neutron capture process path, because typically you are capturing lots of neutrons at a time and staying far away from stability, and happens on very short time scales. So the whole thing can play out in a matter of seconds, for example. So hopefully that answers your question.
Thank you.
Yeah.
This is perhaps a naive question, but the plot there suggests a saturation for the number of neutrons that can be produced in the unexplored territory. Is there a critical, so to speak, a critical neutron number one could expect that you can't go beyond?
Yeah. So at some point, you start destroying the things that you've produced by photodisintegration. And you achieve a balance between neutron capture and photodisintegration, and that balance is affected by, for one, the temperature, which is providing you with these photons to destroy the nuclei. So that's certainly an important factor, but also by the Q value of the reaction, which means the mass difference between the thing that's capturing the neutron and the thing that's destroying it. So if that Q value becomes very small, then it becomes relatively easy to provide enough energy to destroy a particular nucleus. And then there's some vertical portions here, which are actually points of particular stability. There's certain magic numbers of protons and neutrons for which nuclei tend to be particularly stable, and that's where you get these vertical lines.
Thank you.
Okay, good questions. Okay, so stellar reaction rates when we're involving charged particle reactions. So nuclei are positively charged, and if you want to have a nuclear reaction between two positively charged things, there's a challenge, which is that they will repel each other by the electrostatic force. And so I guess all of you have a good understanding of how the force looks. It's 1/r² force, or 1/r potential, and then so it's shown right here in the bottom left figure. And so that's this part of the curve here. But there's another force, the strong nuclear force, which enables nuclei to stick together. Okay, so if nuclei get to, or nucleons get very close to each other, then there's this attractive, strong nuclear force that makes them stick together. And qualitatively, sometimes I think of it as something like Velcro. So if you have the two sides of Velcro, they don't know about each other until they get close enough that they just kind of stick. And so somehow you have to get the nuclei together close enough to stick. And the challenge is, classically, you have this Coulomb barrier that you have to overcome to get in to the portion of the potential that's attractive. And in most stars, you don't have enough energy to overcome that Coulomb potential, but you can actually quantum mechanically tunnel through that Coulomb barrier. That's a fully quantum mechanical effect. And the nuclear fusion in stars relies on that. And so if you look at the figure on the right-hand side, there's two important distributions. Well, for one thing, tunneling through that barrier depends on the energy of the incoming particle. So maybe in the simplest case, if you consider one of the nuclei to be stationary and you have a proton coming in, and you want to consider whether it's going to be captured by that nucleus or not. If the proton has more energy, then it's going to be higher up in this Coulomb potential, and it has to tunnel through just a thinner amount of the Coulomb potential, and so the probability increases. And so on the right-hand figure, the red line shows the probability as a function of energy to tunnel through the Coulomb barrier. So it increases with energy. Okay, and there's another distribution shown here, which is the thermal distribution of the kinetic energies of the nuclei in the star. And so that is, to a good approximation, a Maxwell-Boltzmann distribution, which some of you may have already seen in your statistical mechanics or thermodynamics courses. It's the same distribution that describes the kinetic energies of particles, air molecules in this room, but at higher temperatures. Okay, so it has this characteristic shape, and it has a high energy tail. So some of the particles in this high energy tail actually have enough energy to tunnel through the Coulomb barrier. And when you convolute these two distributions, you get a range of energies where it's most probable to actually capture a charged particle, and that's called the Gamow peak. And that's typically where we want to measure a nuclear reaction. It's the range of energies where we want to measure a nuclear reaction. And so the experimental approach when we're using a stable reactance is to measure the cross section, which we call sigma, as a function of energy for the most important reactions first, as low as possible in energy, and then often we have to extrapolate. So the cross section is just the probability that two nuclei are going to fuse as a function of energy. And the cross section really falls off as we go to low energy, because that probability to tunnel through the Coulomb barrier kind of just drops to zero. And the cross section, if there's nothing interesting going on in the product nucleus or the compound nucleus, the one that you make when these two things fuse together. So if there's no nuclear states here that can act as resonances, then it tends to be a smooth curve. But sometimes there's nuclear states there that can cause resonances where the cross section is strongly enhanced. And all of this is taking place below the Coulomb barrier. So just schematically, the Coulomb barrier is up here in energy or so, and typically you can measure down here, and then often you have to extrapolate into the region of interest. So the way these direct measurements happen, kind of generally and abstractly, looks like this. You have an accelerator that usually of protons or alpha particles, where alpha particles are the nucleus of a helium-4. This accelerator delivers those particles to a target. Okay, so the target's the thing that is going to be potentially capturing a proton or an alpha particle. Okay, and so maybe the target could be a piece of aluminum foil. Then in that case, it would be aluminum 27, and you would be bombarding it with a proton.
What's the source of protons?
The source of protons would be some kind of ion source in the accelerator. So you would take some hydrogen gas and rip some electrons off of it, or even potentially add some electrons to it. And then once it's charged, then you can manipulate it with electric and magnetic fields to accelerate it and deliver it to a target.
What's the energy of the projectile?
Oh, for these astrophysical measurements, it would be typically hundreds of keV, maybe up to a few MeV, mega electron volts, that is. So you deliver them to a target, and then you get a nuclear reaction happening. So we'll call the beam little a, and the target big A, where the big A is usually going to be something, some nucleus that's heavier. in mass, has more nucleons in it, and then you're going to produce some reaction products. Okay, so some completely different nucleus, big B, and then usually some other light particle or a gamma ray. So the light particle B or a gamma ray. So you have some detectors there then to detect and count the gamma rays or the light particles. And that ultimately tells you the cross section, and then sometimes you need some shielding to make sure you're not going to get backgrounds of various kinds. So that's kind of a traditional nuclear astrophysics experiment to measure a nuclear cross section, and this is relevant for that quiescent stellar.
In nuclear astrophysics, in the previous slide, I'm just curious. Could one use a projectile as a deuteron system as opposed to protons or alpha particles?
Yes, and actually I will address a case similar to that a little bit later on. But yeah, you can use a deuteron for sure. Yep.
Okay.
So for those who don't, for those who don't know, a deuteron is the nucleus of a special isotope of hydrogen that has both a proton and a neutron in a bound state stuck together. Yeah. So yeah, good question. Okay, so why would we want to make beams out of rare isotopes? Well, for astrophysics, for events that tend to happen quickly, so those are kind of like transient astrophysical events, things that appear in the sky and then disappear very quickly. Often those are explosive events involving exotic nuclear processes with timescales that are very short. And in those exotic nuclear processes, we can produce radioactive nuclei that then can undergo subsequent reactions before everything decays back to stability. And often we have to understand the interactions of those rare nuclei or their properties to really understand what's going on in a core collapse supernova, a thermonuclear supernova, a classical nova, or a neutron star merger for that matter. Okay, but if we want to study proton and alpha capture reactions on unstable isotopes, then we can't use the usual method because before we were talking about using an aluminum foil, for example, as the target. That's the heavy thing. But if we still want to measure proton and alpha capture reactions, but on something radioactive that has a half-life of 1 second, then we can't make a target out of it and bombard it with a proton and alpha beam. So what you have to do instead is make a beam out of the radioactive thing and bombard a target that is made out of protons and alpha particles, so hydrogen or helium. If those are the reactions that you're interested in. So we call that inverse kinematics because it's the reverse situation where normally we would be using a light beam and a heavy target. We're now using a heavy beam and a light target. And another thing that we do a lot of is we use so-called indirect techniques, which means we don't actually measure the reaction of interest directly. Often that's going to be too hard. So instead, we study the properties of the rare isotopes that are involved, and we piece together key nuclear structure information, for example, to determine a reaction rate. So how do we do this in a practical sense? So the lab I'm sitting in right now is the National Superconducting Cyclotron Lab, which is soon to be the facility for isotope beams. We're kind of in this transition period. So first, I'm just going to quickly talk about how we've done things at NSCL and how this FRIB facility improves upon that. So the first thing we do is we make a beam, just like we had done before. So first of all, we ionize it, and then we accelerate it. And we have done that with a pair of cyclotrons in the past, up until about a year ago. And now we're accelerating a heavier beam, not just protons and alpha particles, but something that has lots of protons and neutrons in it. And the beam is going to be many billions of nuclei per second in the beam. This beam is stable. Okay, we call it the primary beam because it's the first beam that we're dealing with. And then it goes and strikes a target, which is a foil. And often we've used beryllium as this foil. And every once in a while, one of those nuclei is going to hit another nucleus. It doesn't happen that often because nuclei are really small and they're not occupying a whole lot of space in that foil. but sometimes it happens. And we like it when it does, because then it breaks into pieces. And some of those pieces are hopefully the ones that we're interested in doing experiments with. So they might be radioactive nuclei or those rare isotopes that we're interested in doing experiments with. But it's kind of a messy process. So, you can see in the middle figure here that, we're producing lots of different things and some free protons and neutrons. And ultimately what we'd like to do, particular nucleus we're interested in for our experiment, and to just deliver that one to the experiment. Sometimes it's less than 1 nucleus per second, but sometimes we can do something useful with even less than 1 nucleus per second. But to do
Just
that,
a quick question.
Yep.
Chris. What's the thickness of the foil? The mass thickness?
Oh, the thickness of the foil. Geez, I don't remember exactly the thickness of the foil. But we would consider it to be a transmission target. So it's thin enough that these nuclei can fly through. The beam nuclei can fly through, but thick enough at least, and so that the ones that are produced can exit. But thick enough that we produce enough reactions that we produce enough of the thing that we're interested in. So I don't want to give you an exact number because I just don't have it in the front of my head.
Okay.
And I've actually, it's made out of, like I said, it's made out of beryllium, and only handle beryllium anyway.
Yeah.
Yeah,
Yeah, I imagine it's on the order of millimeters or so.
probably. Yeah.
You're saying very few, sorry, somebody else going.
Sorry, Chris, maybe I can jump in because I've done a few simulations and used beryllium targets, for the NSCL. It's typically a few millimeters we use. It depends on what you want to, of course, create. But as to what the energies we're at, a few millimeters.
Great. Thank you, Clementine.
Yeah, I thought that very few beam nuclei hit a nucleus in a target and fragment becomes a new element. Are we talking about the fragments? That's new element?
Yeah, the fragment is the new element. If the nucleus doesn't, so if the beam nucleus doesn't interact with the nucleus in the target, then it will just stay the same. Well, it will stay the exact same species. The fragments in general, they could be the same element in a different isotope. In that case, it would just lose some neutrons, or it could be a completely different element.
Does it not bring any, radiation that are inside the nucleus, new particles?
Well, there's definitely radiation. I mean, you can see, for example, here, you're producing these free neutrons and protons, and neutrons are a particularly problematic type of radiation. Usually, we use lots of concrete shielding, and nobody goes near the production target when the beam is hitting the production target.
CERN in, I guess, Switzerland, they expose nuclear emulsion plates to K- meson that used as projectile, and a lot of fragments and many elementary particle type things are produced in the nuclear emulsion, other than the fragments of the big nucleus.
Yeah, we're not. Yeah, so at these beam energies, which are less than half the speed of light, we're not able to produce mesons like that. So we're working this. This field is it's considered low energy nuclear physics, and what you're describing would be high energy nuclear physics or high energy particle physics.
I mean, how do you what's this difference between low energy, medium energy, high energy? I'm saying, does it depend upon any standard classification?
It depends on the energies of the beams. I mean, typically in nuclear physics, we're dealing with kilo electron volts to mega electron volts. Intermediate energy, you're dealing with giga electron volts, and then high energy, you're dealing up to tens of tera electron volts, essentially. Yeah, sure. Okay, so we need to separate out these nuclei somehow, and so we can use what's called a fragment separator for that. And the principle is kind of like a prism. Okay, so in a prism, you're separating out wavelengths of light, and in this case, we're trying to separate things out by the ratio of their momentum divided by their charge, and that's what a dipole magnet can do. So we have this chicane shape that has 4 dipole magnets, and there's a real one here. It's the white thing in the picture down here, and then we have some beam focusing elements in between, and ultimately by putting the beam through this chicane on the other side, we can get a reasonably pure beam of one particular isotope. So we get this wide variety of nuclei from the collisions with the target entering, and we go through, and this device, which is called the A1900, filters out the one nucleus that we're interested in, then delivers it to an experiment. And so we call
kinematics, do we have to identify what was the target?
Do we have to identify what was? I'm sorry, I don't understand.
Yeah, in the kinematics, I see. Do we have to identify what target was hit?
Yeah, I mean, so that's well defined. I mean, that's the beryllium. So beryllium 9. I mean, it's practically always the case that it's going to be that has been beryllium at NSCL, so usually we do simulations to figure out what the optimal settings are for all of these electromagnetic devices like these dipole magnets to deliver a particular nucleus. So we know the beam energy going in, and we know the beam species going in, and we know the target species.
I see.
And from that, we can calculate the kinematics going out. And from that, we can make a good guess as to what electromagnetic settings we should use here. And that's what we'll typically start with, that best guess. And then it'll take some tweaking at the beginning of an experiment to make sure that we're getting the nucleus out that we wanted.
One more question, MC. Is there any way to detect the neutron emission in the reaction?
Yeah, we could detect the neutrons. I mean, I'm sure there are neutron detectors down there just for safety reasons to know how strong the neutron field is, but we don't do any science with those neutrons. Okay, so ultimately, that beam gets delivered to experiments, and experimenters can do all kinds of things, whatever they can imagine, and there's all kinds of different setups around the laboratory. It's kind of like a big playground for experimentalists. And these are just some examples of detection setups. So the MONA array is an array of scintillator panels that generate light when neutrons hit it. So what will happen with those MONA experiments is that this radioactive beam flies toward another target. So this is now a second target, and induces another nuclear reaction to make something even more neutron rich than the beam is, that promptly splits apart because it's unbound, and some charge fragment is emitted that gets analyzed by a magnet and a detector, and then some neutrons fly toward this wall, and they can piece together what exotic nucleus was produced and in what excited state it was produced. HIRA does something similar with charged particles. So it tends to study nuclei that are on the proton-rich side of stability. So ones that have more protons than neutrons, and then those free protons fly toward this detector and get detected. On the right-hand side is a big 2-story tall magnetic spectrograph, and you can see some platforms here where people can walk around, but embedded behind the platforms here is actually a really big pair of dipole magnets that can analyze the charged particle products of a nuclear reaction involving involving a rare isotope. So the rare isotope beam comes in from the bottom left here, hits a target in the target position here, and usually there's a detector around the target position to detect, for example, gamma rays that are produced when the nuclear reaction happens, and then the charged particles, those are the nuclei that are produced in the reaction, get analyzed by this magnet and detected up here, and you can identify the particular nucleus that corresponded to the radiation that was emitted at the target position, and tag it in that way. And so when I start talking about the FRIB facility, you'll see that there's an updated version of this planned for FRIB and optimized for FRIB. So this is kind of a floor plan of NSCL today. You can't see the scale here, but this is probably several hundred meters across. There's office space in gray. And then we had these two cyclotrons here that were making the primary beams. Here's that A1900 fragment separator in that chicane shape. And then it delivers these fast fragmented beams to experiments that are mostly in this bluish color here. And I haven't talked yet about some of the other things that we can do with these beams, but I will. We can also stop them or thermalize them and deliver them to experiments at low energies. And then we can also reaccelerate those thermalized beams and use those for experiments. Or produce more of the nuclei that we can already produce at NSCL. And the solution is to fragment more nuclei with the next generation facility for isotope beams. So that's a $730 million project that was actually going to become operational in 2022, which is pretty exciting. And so what it's doing to our existing facility is this. The cyclotrons have already been essentially turned off. And for the last several years, we've been building a linear accelerator to produce to replace those cyclotrons and produce beams that are somewhat higher energy but have a lot more particles in them, which means the beam power hitting a production target is much higher, and that just means we make more of every nucleus that we're trying to make per unit time. And so we have 3 linear accelerator segments. We make some ions up here. Actually, it's at ground level where we make the ions, then we send them down 3 stories underground. This whole thing's underground because it produces a lot of radiation, and the ground produces some natural shielding for that. And it goes down this linear segment 1, the next segment 1 here, and then it folds over on itself. So the beam gets bent down segment 2, so 180 degrees, and then bent again down segment 3. So it's got this kind of paperclip shape, the linear accelerator does, and it's just a compact way of building it. And then it gets delivered to the production target. Now we're still 3 stories underground. And then there's a fragment separator, which actually reuses some of the components of NSCL's A1900. And then we deliver actually to the same experimental areas where NSCL was doing experiments. So that's kind of an efficient way of doing things. So this facility for isotope beams, we call it FRIB for short. Some people call it FRIB, is a very near future user facility at Michigan State University. User facility means that anybody who wants to do an experiment, who has a good idea that is scientifically impactful and feasible, can have a shot to do their experiment here. All they have to do is write a proposal that will be evaluated by a committee. So it's funded by the U.S. Department of Energy, and there were contributions also from Michigan State University to this. There's at least 1,400 users worldwide, and the main feature is a 400 kilowatt beam power for all ions in the primary beam. And just for one example is 5 times 10 to the 13 uranium-238 per second can be delivered to the production target. So we're using this in-flight method, which is the one I had described for NSCL. It's the same method fundamentally. We're just using a different type of accelerator to produce the primary beam. And it enables a rapid development time for any isotope. So just, a day or 2 at most. We can, in principle, study all elements. This is not a very chemistry dependent thing. And short half-lives, things with very short half-lives can be studied and delivered to experiments before they decay. And we can use fast, stopped, or reaccelerated beams. So I mentioned those briefly, but I'll talk about those more soon. Now, I'm trying to remember where the next question was supposed to be. Anna, was there supposed to be one after slide 12?
Yeah, so how about now?
Yeah, let's do it.
Anybody else? We have 4 people who have responded.
Okay, we've got 5 now. Okay, so let's move on. So that's great. Thank you for answering the question here. So I never really gave you the answer to this question. I just wanted to see what your intuition was, and yeah. So actually, the key specification for this new accelerator is actually the beam power, and it's really the beam power that gives us more rare isotopes, more so than the beam energy. You know, by less than a factor of 2, and that's really not the main thing that is providing us with more isotopes. It's the amount of particles in the beam. Okay, so this new accelerator is providing us with more particles in the beam being delivered to the production target, which gives us more chances to make some of the rare isotopes that we're interested in. So this 400 kilowatts is in comparison to on the order of 1 kilowatt or less for the existing or previously existing NSCL facility. So it means that we're going to be able to produce almost 3 orders of magnitude more of everything, which is really exciting. And that really translates into being able to produce some things that we've never been able to produce before. So what can we do at FRIB? Well, we can study obviously the properties of nuclei. Some people are primarily interested in you know, how protons and neutrons configure themselves to make a nucleus. We can also test some fundamental symmetries of nature. So that basically means doing particle physics at low energies. So if we can measure certain things very, very precisely, then we can place limits on new forces and new particles, or potentially even discover new forces or new particles that are fundamental. There's some societal applications and benefits of using rare isotopes. So those include medical applications, or detector technologies that can be developed while studying rare isotopes that can be useful for things like national security, for example. But today we're focusing obviously on the astrophysical processes. So that involves the origin and evolution of the elements, and explosive environments, like I mentioned, novae, supernovae, X-ray burst, or neutron star mergers, and properties of extreme types of stars like neutron stars that are very dense at nuclear density. And so what's the reach of this on our playing board here? Well, this plot shows it. It shows how many of each of these types of nuclei we can make per second, and it's a log plot here. So orange is like 10 to the 10 per second. Red is much more than that. So each of the red squares is one of the primary beams that we're going to use to produce the rare isotopes. And so you can see if we're close to one of those, we can really make lots of everything. But there's lots of potential primary beams, which means we can cover essentially the whole nuclear chart and push out very, very far, even out to this R process path that we couldn't cover before, and all the way up to the proton drip line, which is where protons are no longer bound to the nucleus, and out to the neutron drip line up to a certain mass number, which is all pretty great. And so the accelerator is going to ramp up gradually. So next year, we're actually going to be doing experiments with 10 kilowatt primary beams, and then a year later with 50 kilowatt primary beams, and then a year after that with 400 kilowatt primary beams, so the full power. So that's pretty exciting. You know, I came here 10 years ago largely because I knew this facility was going to be developed here. And so I've been focused on doing experiments with the existing facility while I was here with NSCL, but I've been watching this thing get developed and built as I've been here, and it's made amazing progress. The whole thing's been on schedule and on budget the whole time, which is pretty amazing for such a big technical project. But the groundbreaking for the building that holds the accelerator and the target hall was in 2014, and there you see it in snowy March in 2014 on the campus of Michigan State University, and the building was finished in 2017, and ever since then technical construction has been going on, which is exciting. And so this is a picture even taken a few years ago, a panoramic view of the linear accelerator cryo modules inside that new building. Ultimately, this accelerator is going to be able to accelerate uranium-238 with energies of no less than 200 MeV per nucleon. And we already talked about the beam power of 400 kilowatts. And in the future, next 10 or 15 years, we hope we can upgrade this to 400 MeV per nucleon, just to give a bit of a boost in production. And that would involve adding extra accelerator modules in this portion of the paperclip, because at the moment there are none, and the beam is just going to drift through that area. And there are also provisions to upgrade to a different radioactive beam production method called the ISOL technique, which I don't have time to talk about today. So one neat thing about the project was that the technical construction and the commissioning, that means the testing by putting beam through the accelerator, was interleaved. And so they were both happening at the same time as more accelerator modules were put in. And it's nearly complete now up to the target position, which is exciting. So once you hit the target, first of all, you're going to make a whole lot of radioactivity. Okay, and so that's why it's good that it's 3 stories underground. But with this high power beam, you have to worry a lot about the heat that's going to get deposited in the target. And so it's no longer a beryllium target now. The idea is to use a carbon target instead. And so these are actually wheels of carbon, and there's about 5 of them stacked on each other. And the beam will impinge upon these wheels and go through all of them, and the wheels will spin so that the heat is getting deposited over a greater area. So it's not just one spot that's heating up and getting destroyed. The unused beam is going to go into a water-filled rotating beam dump. Okay, and in there, there's going to be nuclear reactions that produce all kinds of things, and those things can be harvested. So if you have some things that have half-lives of, a few days or weeks, then you could extract them from the water and use them for experiments related to medical techniques, for example, or whatever else you can imagine would be useful. So there's a facility being developed here for that as well. This part is under construction. I've been down there a week ago, and most of the pieces are actually in place. So it's really almost done, and it's supposed to be done by the end of the calendar year. So I didn't tell you much about the stop beams yet. How does that work? How do we stop the beam? If we have this fast rare isotope beam, there's various ways to stop it, but we want to be careful if we actually want to stop it and deliver it somewhere else. And so if we plunge that beam into a noble gas volume, then the beam won't undergo any chemistry with that noble gas to first order, and it will just stay ionized. And with a combination of gas flow and electromagnetic fields, we can bring those ions to a nozzle and then accelerate them to a few tens of keV, which is essentially enough to keep them from falling out of the air by gravity, and deliver them to low energy experiments where we can do various types of precision measurements. We can do laser spectroscopy to look at the atomic properties of isotopes as a function of neutron number. Or we can measure their masses very precisely with a Penning trap, for example. Most of the gas stoppers we use so far are linear, which means the beam just comes in along a straight line and slows in the gas and is extracted on the other side. But there has also been developed a brand new technology, which is a cyclotron gas stopper, which uses a magnetic dipole field and a volume filled with gas inside that dipole field. And then the particles come in and lose energy and spiral in toward the middle, and then you can extract the ions. That has been installed, and the commissioning has at least been started on that. Now, once you stop them, you might actually want to reaccelerate them. And so you might wonder, why in the heck would you go and reaccelerate them when they're already moving so fast in the fast beam? And one of the reasons is that you can get a much higher quality beam if you're starting the ions from rest. So instead of having this fragmented beam that has initially flown out in a cone with this kind of messy spread in momentum vectors, you can make a beam that's the size of a pencil, essentially, with a very well-defined energy, and deliver it to experiments. And you can also deliver it at much lower energies than you could with the fast beam. And it's actually those low energies at which the astrophysical reactions tend to take place. And so this is useful, particularly useful for nuclear astrophysics experiments. And so this is just showing the linear accelerator that we call the reaccelerator, that can deliver beams to various experimental energies at energies either up to 3 MeV per nucleon, we call it RIA 3, or 6 or 12 MeV per nucleon. RIA 6 is now operational, and RIA 12 will hopefully be operational in the future. And those all have their own specific types of experiments that they're ideal for. So, so this is then just a view of the FRIB experimental areas from above, just a somewhat different view than we saw before. There's the fragment separator. It's just curved. It's not in that chicane shape anymore. There's the old cyclotrons that we're not going to use anymore for this purpose. The fast beams could be delivered to these various fast beam areas that are very similar to what we had before. This one in red happens to be new, and I'll talk about that in a moment. We have the stop beam areas over here, and then we have the reaccelerated beam areas over here. So that's RIA 3, and then that's RIA 6. And the isotope harvesting takes place near the target position, of course.
And it's time for another question.
Oh, thank you.
All right, I'm gonna end it.
Okay. Okay, thanks, Anna. Yeah, so so everybody got it. Indeed, we offer all those types of beams. So stopped, reaccelerated, and fast beams, and even isotope harvesting. So, so I'm just going to say a little bit about some of the major experimental devices that are at FRIB and their relation to nuclear astrophysics experiments. One is a big project called the Gamma Ray Energy Tracking Array, or GRETA, and it is germanium detector. So germanium is really good for detecting gamma rays with very high resolution. And so it's always nice to have germanium that covers a large solid angle to optimize the efficiency of an array. But one of the challenges we have when we're doing these experiments that in inverse kinematics with a heavy beam and a light target is that the residual nucleus that emits the gamma ray is going to be moving at a high velocity. And that means that the gamma ray is going to be Doppler shifted. And if we want to correct for the Doppler shift, then we have to know where it interacted with the detector. And so that's what this array is able to do. So it's able to determine the interaction point of the gamma ray, the first interaction point of the gamma ray with the germanium in order to make that Doppler correction. They can do that to within a few millimeters. And then that recovers the intrinsic energy resolution to a good approximation of the germanium. So this has been a huge project that's been in the works for over a decade, and there's a precursor to this called Gretina, which is the same thing with just less germanium detectors. And here's a picture of Gretina here with sort of the incomplete sphere of detectors, and that's already been used for experiments at NSCL for a long time. And so for nuclear astrophysics, one of the things we can do with a setup like this is to do indirect studies of proton or neutron capture reactions for the rapid proton capture process, which is similar to the rapid neutron capture process, but on the proton-rich side, or the R process, which is that rapid neutron capture process. And the way that we can do that is we take some nucleus A and bombard it with a deuteron. So that's hydrogen 2 that came up before. We had a question about that, and produce a product nucleus and a neutron and a gamma ray. Okay, so what's happening there is we are just transferring one of the protons that's in the deuterium nucleus onto nucleus A and making nucleus B. And so that's a surrogate for a proton capture, and we can get a lot of information on the proton capture from that. And similarly, from a reaction where we start off with a deuteron and we go to a proton, that's a surrogate for neutron capture, which can be useful. And we can also study with Gratina so-called charge exchange reactions, which is where you're exchanging a proton for a neutron or vice versa in the nucleus. And that has some analogy to weak reactions, weak interactions in stars, for example, like electron captures in stars. So electron capture decay is an example of weak interaction. It competes with beta decay, similar to beta decay. And so
the charge exchange reaction can be studied in a gaseous medium.
Yeah, it in principle it can be studied using a gaseous medium. Yeah,
but your facility will allow it. All this.
Yeah, our facility could allow it to be studied in a gaseous medium. I mean, do you mean a gaseous target, or with a gaseous detector, or some combination, or what?
Gaseous target.
Yeah. In principle, it can be studied with a gaseous target. Yep. Another question you said?
Do you have any collaboration with any HBCU?
With any agency, you said?
HBCU, historically Black University and colleges.
Oh, yeah. So I think there's a number of collaborations with historically Black universities and colleges. Yep.
If someone is interested to work with
yeah. So good question. With a little information, opportunities come here, but is this the insight program that more information about that at the end of the talk?
Okay, we'll wait for that. Thank you.
Sure.
Just real quick, Chris. For the Wrede detector, you have to cool down the germanium to cryo temps, obviously.
Yes.
How is that handled? I mean, I guess what I'm getting at, this seems to be, and you mentioned that this has been ongoing for 10 years or so. That seems to be non-trivial.
Yeah. So I think they have an automatic liquid nitrogen filling system. And probably the detectors have to be filled every 8 or 12 hours or something like this. And so with large arrays like this, usually there's some kind of automated filling system that's never perfectly automated, right? Somebody still has to check and make sure that it's working. So there's usually somebody on shift to check and make sure that each fill has happened properly and sort of supervise that. But yeah, it's automatic liquid nitrogen filling systems, and the lab has liquid nitrogen infrastructure to provide that.
Was there a rationale for going with liquid nitrogen as opposed to electrical cooling?
Oh, good question. We were just discussing something similar in my research group, because we're developing a setup that uses some germanium detectors, and we've chosen to use electrical cooling for our detectors. But ours is not a giant array. It's just a few detectors that we want to be able to operate conveniently in our lab space. And since we're a smaller collaboration, we decided that the electrical cooling was better for us, because we can just set it and forget it, essentially. It's lower maintenance. But I know some people are opinionated that liquid nitrogen is preferable because I don't know all the reasons, but I'll just say that some people are pitting that it's preferable. I mean, it always works, I guess. Let's put it that way. You know, if you have the liquid nitrogen, it will always cool down your detector. So in that sense, yeah, as long as you have people to run it. So it seems to work better for, you know, large arrays and large collaborations, I would say.
Okay. One last quick question. Any issues with radiation damage on the on Wrede as it relates to Wrede?
Oh, that's a good question. Experiments with Wrede. So I don't know. But I don't know. I also haven't seen anything, you know, and I haven't seen anything in anything that anybody's presented to indicate that the performance is really degrading of the Gratina detectors that have been used for almost a decade now. But you know, the beams will get more intense, and you know, there will inevitably be more radiation damage. Whether it's significant or not, I'm not sure.
Okay. Thanks.
Yeah. So do you have to use radiation base?
In the lab, so I got mine right here. There's certain areas in the lab where we must be wearing it to go, but when we're in office space, we don't need to take our radiation badge. Yeah. Okay. So Wrede, the optimal place to put it is in front of something like the S800 that we saw before. That's that big magnetic spectrometer that analyzes the residual reaction products. It can also go literally in front of the S800, which will still be there. But we have this newer version that I'll talk about in a moment called the high rigidity spectrometer. It could also go in some of the reaccelerated beam areas. In those areas, you don't quite get the advantage as much of the Doppler correction, but you certainly get the advantage of the high efficiency and the 4 pi coverage. So the thing I was alluding to, the high rigidity spectrometer, so it is the follow-up to NSCL's S800 spectrograph, that 2-story dipole magnet that I mentioned before, but it's optimized for FRIB's fast beams. And it's in this whole new experimental high bay that's outlined in red here. And it kind of fits in the middle of a bunch of existing buildings. And this picture on the right-hand side was taken a few years ago when this high bay was just being constructed. And now it's actually there. Okay, so the high rigidity spectrometer itself isn't there. It's kind of a 10-year project, quite a large project. But the hall has been built, and we have every expectation that it will move forward. And so the benefit is that since the FRIB beam energies are going to be higher, especially after the energy upgrade, to make full use of that, we want a magnet that is optimized to have the rigidity, so to be able to handle the momentum over charge of the reaction products from those beams. And it turns out that the gains of this HRS get bigger and bigger the farther and farther away we go from stability. So the places where we have the hardest time making more and more isotopes. So that's kind of ideal. And then HRS will have these ancillary detectors, the things that typically go around the target position where the nuclear reaction is actually happening. And Wrede is one of them already mentioned. And there's a boatload of other ones here, and too many really to mention. But some selected nuclear astrophysics that can be done there are heavy ion collisions to study the nuclear equation of state that's relevant for neutron stars, for example, or for core collapse supernovae, and also mass measurements that are kind of kinematic mass measurements that combine the magnetic rigidity in the spectrometer with the time of flight of the beam over a long path to pin down the mass to, you know, a few hundreds of keV for the R process, because even some fundamental information out that the R process path is not known. A lot of fundamental information is not known. So sort of the first step is determine the masses and half-lives of the things out there, and then try to measure more detailed information after that. And then one of the simplest things you can do with these rare isotope beams is just measure their decays. And there's lots and lots of information that we can get by measuring the decays. And that's actually what my group does. And so there's a collaboration, the FRIB Decay Station collaboration, that is trying to develop a setup that is going to be a general purpose decay setup that can accommodate practically any type of detector that can be used for decays. And there's lots of different types of detectors, because after a beta decay, you might get some charged particles emitted, like protons or alpha particles, or of course the beta particles themselves. You might get gamma rays emitted from the daughter states, because the beta decay can often populate excited daughter states, and also neutrons, because your beta decay might populate neutron unbound states that then go and emit neutrons. And so the decay station can operate with fast beams, and that's what it will do first. So you just take that fast beam and deliver it, let's say, into a stack of silicon detectors, for example, or some other central detector, and you enable them to decay there, and then you can detect, for example, gamma rays that are emitted following the decay using some germanium detectors. It can also operate in a stop beam area. So some experiments might operate optimally in the stopped beam area, albeit with a little bit of an efficiency hit for how much of the beam you can get through the gas stopper to the stop beam area. So for the first experiments will be done with fast beams, and then subsequently there'll be a campaign for stop beams. And these are just some schematics of how this looks, and it can look lots of different ways, because you can use lots of different types of detectors or combinations of them in this modular system. But without getting into details, I'll just say that we can measure half-lives, branching ratios, beta decay strength functions. So how often do you beta decay to various excited states in the nucleus? Properties of resonances that might be relevant to astrophysics, and also statistical properties of nuclei that are useful for piecing together reaction rates in the RP process and the R process. And last one I'll mention is the SECAR recoil separator. So one of the first experimental concepts we showed before was the traditional measurements where you took a proton beam or an alpha beam and impinged on, let's say, an aluminum foil and measured the reaction products. Well, I also mentioned that if you want to try to do a similar type of measurement involving a radioactive species as the reactant, then you need to do something completely different, like an inverse kinematics measurement if you want to measure it directly. Okay, and so that means then that you have this radioactive beam impinging upon a hydrogen or helium target. Okay, and so this SECAR recoil separator is designed to do exactly that. The challenge with these measurements is, one, producing that radioactive beam, and then two, being able to pick out the reaction product and actually measure it. And the reason it's so challenging is that this radioactive beam in the RIA3 Hall comes in. It's one of those reaccelerated beams. And so it's going to have an energy on the order of some hundreds of keV per nucleon for a proton or alpha capture measurement. It's then going to go in and hit a hydrogen or helium gas jet. Okay, so all of these beams are evacuated. The beam lines are evacuated, and the beam is passing through this evacuated beam line. But at that low beam energy, you can't afford to have your beam go through containing walls for a gas volume. And so instead, what is done is a jet of gas is shot through the vacuum and collected on the other side, and that serves as the target for the experiment. And so that's a big device, the whole gas jet target, because there are all these pumps that are used to recirculate and compress the gas to make the jet. But the rest of this is the SECAR recoil separator, and what it does is it electromagnetically separates out the reaction product from the beam, because the beam is all flying forward. You have this heavy beam hitting this light target, and so even the unreacted beam is all going to fly straight forward into here, and the reaction products are also going to fly forward in some relatively narrow cone. And this electromagnetic separator is designed to only transmit the reaction product to the end and not the unreacted beam. And so you just count them here in this focal plane detector. So this is this construction is completed of this, and the commissioning is well underway. And last thing I'll just mention is the JINA-CEE. It's an NSF Frontier Center, and it's actually based here at Michigan State University. This may be a somewhat outdated plot, but it shows a lot of the connections that are facilitated by JINA-CEE and nuclear astrophysics, both nationally and internationally. And so you know, not only is this a nice place to get lots of rare isotopes to do beams, it's also a nice place to collaborate on nuclear astrophysics, which is an intrinsically interdisciplinary field. So getting toward the end here, did I skip a question? Are we at a question right now, Anna?
There was one at the end of last slide,
okay,
so I can show.
Let's do that one.
Come on, pick your favorite.
You want a t-shirt?
Yes,
This could be the tiebreaker for the t-shirt.
Okay, I'm gonna end it.
Okay, sounds good. Okay, so most of you said that rare isotope beam facilities are essential to the study of nuclear processes in exploding stars. And in principle, rare isotopes might be relevant to any of these, but I tried to focus today on exploding stars in particular. So thanks for participating in the polls there. So, you know, if you're interested in anything I've been talking about, you know, whether it's the science of nuclear astrophysics or the technical aspects of accelerator science or radiation detectors, there's lots of things that you could do at FRIB. There's lots of undergraduates who work here at NSCL and FRIB, both from the department here, you know, of physics, astronomy, or engineering or chemistry here on campus, but also lots of people from outside of a campus. So, for example, we have a research experience for undergraduates program that I've linked here in case you're interested in doing something in the summer. There's also the Insight program that Henrik might be able to say more about. But, you know, all these types of things as an undergraduate, these research experiences as an undergraduate are great for preparing for grad school or for joining the workforce. We also happen to have the #1 nuclear physics graduate program in the whole United States, according to US News and World Report. And, you know, that's largely because of you know, all these rare isotopes that we could produce and do experiments with. It attracts lots of people here. If you want, you can always peruse the websites of NSCL and FRIB to find some research that you're interested in, or a mentor that interests you. And I would encourage you to just reach out to anybody directly if you find particular interest in what they're doing. And it certainly doesn't hurt if you tell them a bit about yourself. Maybe send a CV/resume and tell them what you're interested in doing. And if you're just generally interested, but you're not sure what you want to do or who you want to work with, we have an associate director for education that's currently Hiro Iwasaki. He's a good person to reach out to. But as Henrik said, you know, and any of us who are giving lectures this this semester would be happy to give you some advice for this talk at one time or another. And thank you all for your interest and your questions and your attention.